Hi, I'm Scott.
I'm Bernie.
We're going to talk to you about the first steps in building a truss bridge. We had mentioned it before during the intro. Okay, Bernie, tell them what our goal is.
Our goal is to design and construct a truss bridge to proper scale, capable of supporting as much weight as possible. Include aesthetic design elements unique to your team, which help make the bridge visually appealing. So what is a truss, you ask? A truss is a structure composed of members connected to form a rigid framework. Trusses are typically comprised of triangular units connected at joints called the nodes. Triangular units which form a truss are slender and straight. The truss is a structure which is commonly used in the construction of bridges. So our hypothesis is if a bridge is built with triangle-shaped supports, then it will be strong to hold more weight than a bridge built with square-shaped supports. So the background on these bridges is they're purposely designed or engineered using geometric shapes that distribute force, thus making the structure strong enough to bear weight. Forces the push from the weight being placed on it. The bridge must bear not only the weight of the materials used to make the bridge, but also the weight of any traffic traveling across it. One shape that distributes force effectively is a triangle. But why is a triangle stronger than a square? Well, the triangle can only have one shape once its vertexes are fixed and connected. A square or rectangle, on the other hand, can have many different shapes without changing the length of any element or disconnecting the vertices. In other words, the square can change shape under load without any of its members breaking or the joints coming apart. A triangle distributes or carries a force differently than a rectangular or square. The nature of a triangle means that it cannot be deformed without breaking a vertex or member. A square can deform to a four-sided polygon without breaking any member or vertex.
Think about a cardboard box. A cardboard box, it might be stiff when everything is held, but it can always be bent or moved. And it can actually completely deform without breaking any point in the box. Hence why boxes can be flattened out. A triangle, when it's all fixed, you can't do that. So now, Bernie mentioned that we were going to build this bridge to scale. Part of the reason that we're going to do it to scale is to introduce you to one of the true basic engineering concepts, and that is, how do you represent an object so that somebody else can build it? And the trick is to draw it to scale. So in this case, I spent a lot of time thinking about a truss bridge, how big it would need to be, and then I drew it to scale using the parts, popsicle sticks, drawn to scale, so that I knew exactly where every piece would go so that I could build it. The proof is in the drawing and laying it out and actually constructing the truss to scale. Now mind you, I did this in a bit of a hurry on my home workbench in about 20 minutes. By myself, no help, just from my scale drawing. So the scale of this bridge is going to be 1 inch equals a foot. That means for every inch that you draw on a piece of paper, it represents 1 foot of the bridge. Now, in order for these bridges to be tested, we have an apparatus, and there's a certain gap that this bridge must span across. And that gap is 20 inches. So in order for the bridge to be able to be tested, it has to be larger than 20 inches. Hence, this bridge is about 21 inches long, or a little bit less. So it will span the gap. Now, when you go to draw something, you might not draw it even at 1 inch equals a foot. You might have to draw it smaller to get it on a piece of paper. We recommend engineering paper or regulated graph paper, something with maybe a 1/4 inch square or 5 squares to 1 inch, whatever you really want. We will end up supplying something. But if you were going to draw your bridge, let's say you selected one square would be 20 feet, or one square is a foot. Well, then you would lay your ruler down and you would count out 20 squares and you would draw your line. So, if I draw this out and said it was going to be 20 feet, let's draw it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now, the popsicle stick has a certain width. Right now, I'm not going to try and draw it to scale, but I'm going to try and be uniform. So I've got the bottom. Now, what we do know is that the popsicle sticks are not an exact, they're all a uniform length, but they're not perfect. So they're just a little bit under 4.5 inches. So if every one of these is an inch, that means that we would have a popsicle stick that would go 1, 2, 3, 4, and a little bit less than a half. And from this end, we have 1, 2, 3, 4, and a little bit less than a half. And then we have the overlap. So how far do we overlap it? Well, that's kind of an engineering decision. You don't want your joints to be tiny. You want your joints to be larger. So if you take a good look at it, you'll see that the overlap is at least 2 of my fingers. I have tiny fingers, but 2 of my fingers in width. So if we did that, 2 of my fingers is just a little bit over an inch, so we'll go a little bit over an inch here, and then we'll go 4 this way. 1, 2, 3, 4. So that would be 1 that way, 1 that way, and there's an overlap in between them. Actually, that shouldn't be, it should be almost 2 inches of overlap. Engineers are free to correct their drawing mistakes too. So, we do something like that, and then we do something like that, and that would be a different popsicle stick. And then we have to have another overlap here. So we'll overlap that way, and they're going to meet up somewhere in the middle. Now, how do you lay out your popsicle sticks? Well, you want triangles. So if you started off and said, I've got a triangle that is, let's make a mark on a ruler and we're going to be uniform. So that's the base of the triangle. Now we want to be roughly in the middle of that and go up that and go up until we hit that. So we're just going to, by the way, you guys probably remember your geometry better than I do, but in order to draw that, I can draw it roughly like that. So if that's roughly the same, that should be almost an equilateral triangle. Your goal is to have good uniform triangles. They don't have to be equilateral, but you do want them to be triangles. So what you need to do is lay out how you're going to build this. You can't just build it off the seat of your pants, you kind of want to lay it out. I laid it out in a computer-aided design program. That said, you should be able to lay it out yourself. I would recommend laying it out dry with just popsicle sticks and seeing how it goes. Or you can draw. You could draw mini ones and cut them out of paper and lay them out. There are lots of different ways to do it. If you have access to a CAD program, that's ideal because then you get something that actually represents the truss. And that was printed out in multiple pieces of paper, cut and taped together to represent the bridge. And so now we're going to start talking about actually building the truss.